Welcome back, everyone, to day 3 of the Cyberbot Educator Workshop. This is March 7th, 2025. As usual, I will go ahead and share the link chat. And paste. So there is the link to the slides, and I'll also add in the shortened link, courtesy of Bitly. There you go. And as the previous days go or went, if you are in full screen and you only have one monitor, just click the view button, select exit full screen, and then tile your screen so you can see the presentation and work with the microbit Python editor. Okay, so today we will be doing a second circuit that that will allow the Cyberbot robot to navigate without coming into contact with objects. We'll talk about the cybersecurity lessons for the Cyberbot and the microbit, project add-ons, educational resources, and classroom implementation. Under educational resources, I'll be showing you the educator-only area of learn.parallax.com where you can access the assessment material. And then classroom implementation will be somewhat of an open discussion. Okay, so infrared light is the topic of today. We're going to use flashlights that shine light forward in a wavelength that is not visible to the human eye. And here is a slide with links to the main activities in the infrared chapter, and I went ahead and posted the chapter, the front page of the chapter to you, and then there's links to the main activities in the chapter right here. But as with all the other ones, if you follow a link to the front of the chapter, then you can click the continue button. Guess I'll have to duplicate this and then click continue. There we go. That way I can show you this video in a second. And then this gets you to the activities in the chapter, and it talks about the visible light spectrum and how infrared falls outside of it, and how it's part of the older TV remotes, the type that you have to point at the television in order to change the channel and set the volume and whatnot. And it even shows a nice little trick of how you can point an infrared remote into a camera and press and hold the button. And for many cameras, you'll be able to see the infrared light flickering because many cameras, cell phone cameras included, detect infrared light as essentially all colors of light. Reason being, the red, green, and blue pixel detectors in most cameras, they have a tendency to detect red and infrared. Likewise, the green ones have a tendency to detect green and infrared. And then same with the blue. And so because R, G, and B are all detecting the infrared light, well, it looks like white light because white is all the colors mixed together. All right, so what we did for homework was build the infrared circuits, and then we're going to test it here momentarily. And so you gathered the parts, made sure that your little lamp had a kind of a rounded dome top instead of sort of a flat dome top, and then put it into the infrared or the LED standoff and the LED shield here, and then snap those together to enclose the infrared LED so that light didn't spill out the sides and back towards the detector. And then the pins should be sticking out separate holes in the underside of the LED standoff. And then after that, we went ahead and built up the circuit here. And what we're going to do next, I think, is I'll show you first a video of how the infrared works once you get it going. So here we go. So essentially, the Cyberbot's rolling towards the box, and the script is making each infrared flashlight flicker. And if that infrared light bounces off the box and is bright enough to make the detectors say, hey, I see flickering infrared light, then those detectors send a certain signal that's a lot like a whisker electrical signal, as in it sends a 0 volts when it detects something, just like the whiskers did, and it sends 3.3 volts to the same IO pin when it doesn't detect something, just like the whiskers did. It just takes a little extra to flicker that infrared light, have it bounce off the box and come back. And so these are set up so that it has to get to a certain distance before the reflected light is bright enough to make the detectors, in air quotes, see the object. So there we go. And so that's what we're going to do with our infrared circuit. But first, we want to test it. First I'm going to go over in painful detail all the electrical connections with you and have you double check all your electrical connections. After that, and only after that, we will then turn on power and let's see, I had a better pointer all set aside for this, and I seem to have put it somewhere in a not good spot that I can't see. Here it is. It was under my bowl of parts. All right. So these two amber lights right here, right here and here, the script that it's currently running is shining the infrared out. And if it bounces off an object and comes back to this detector, the amber light over the P21 label down here will turn off. And then if this detector is reflecting infrared light to this receiver, the amber light above the P20 label will turn off. So if I put an obstacle in front of the light on the right, the P20 light turns off. And then likewise, if I put an obstacle in front of the detector on the left, the P20 light turns off. And that will be the test to let us know that we're ready to move on to the next step, which is going to be using that information in a script to navigate. But first, let's take a nice close look and make sure that we've all got our circuit correctly wired. And I'm not sure which one is going to be best. No, I think it'll be best to do it with the actual bot here. So first off, let's check each So make sure your power switch is set to 0 so that the power is off. And then let's check and make sure that each infrared LED has the longer pair of pins on the higher row. And so the infrared LED on the Cyberbot's left, which is near the top of the screen right now, it's 2 pins. The longer pin is going to be above the shorter pin as it's plugged in, and it's going to occupy the 2 topmost rows of the white breadboard. So I'd like everybody to double check that first. And so verifying that the LED is plugged into the top 2 rows and that the topmost row has the longer pin. Next up, we'll take a look at the other infrared LED. And when we unplug this one, the pins are also, the longer pin is also essentially in this view above the shorter pin. And so it's going, the longer pin is going to go in the second row from the bottom, and then the shorter pin is going to go into the bottommost row. After that, looking at the infrared detector, it does not share any rows with the infrared LED. So it should be, its bottommost pin should be the third row from the bottom, so not shared with either of the 2 rows that the infrared LED pins are in. Next up, what we want to make sure about is that the topmost pin of the infrared receiver is sharing a row with a red wire that's jumping up here to a black socket that's labeled 5V. Feel free to shout out at any time to ask for clarification or ask me to adjust the robot's position so that it's easier to see. So we've got the uppermost pin. That's going to be the 5th row from the bottom, sharing a red wire going to ground again, or pardon me, going to 5 volts again up here. Then the middle of the 3 pins, that's going to be the 1, 2, 3, 4th row from the bottom, is going to share a black wire right there, and that black wire is going to one of the black GND sockets that's in this black header below the breadboard. So not into one of the white breadboard sockets, but into one of the black sockets below the breadboard. Then the bottommost pin of the infrared receiver is the 3rd row from the bottom. And this row will also have a 220 ohm resistor plugged into it. That's the red, brown, gold color code. Normally we just call out red, brown, and then the gold is kind of assumed as being the tolerance for any, for all the resistors in the kit. So I usually just say red, brown as opposed to red, brown, gold. And this red, brown resistor needs to go into P2, the socket labeled P2 right here. There we go. Now, my P21 amber light was not coming on because as I built this, I had my resistors off by 1. So I accidentally plugged in my 220 ohm resistor to P3 instead of P2. And then this other one was in P2 instead of P1. And so my system didn't work until I found and fixed that. So it's an easy mistake to make to be off by 1. So Anyway, the red-red-brown resistor should, its other end should be plugged into the socket labeled P2. Okay, moving down one row. Now we're in the same row, the second row from the bottom, which is the LED's long pin row. That row is going to share with a red, black, red. That's a 2000 ohm resistor. It resists the flow of electricity more strongly than the 220, in fact, almost by a factor of 10. And so this is going in this, the red, black, red resistor is going to the same row as the long pin of the infrared LED. And then on the other end, it's plugging into P1. One other thing is make sure that any of these pins or wires sinks into whatever socket you're plugging it into by about 1/4 of an inch. It's not good enough to just have it sort of like sitting on the top of the socket. It needs to definitely sink in by 1/4 of an inch. Not
Hey,
any
Andy,
further than that. Oh, yes, go ahead.
can I ask you a question about
Certainly.
resistors? Because
Okay.
resistors are the bane of my existence. And it
Oh
has to do with
my.
the fact that I'm like 45 years old and I can't see this stuff. Like I am not 100% sure if I have the right resistor.
Okay,
I
so
think,
one thing you can do for that is use your phone.
okay.
Let me get mine woken up here. Okay, so here's my phone. And what you can do, one way to do it is just simply use your camera and flip around so that you're not taking a selfie. And you can actually normally unpinch and get a really nice close-up of the resistor stripes.
Oh, that's actually a good trick.
Thank you. And then many phones actually have a like a magnifier app, and or rather, some phones have a magnifier app, and you can also go to the app store to get a magnifier app.
Okay,
And
so
there we
I'm
have a
looking at
nice.
this now and I do actually have the wrong resistor. In the
Okay,
whole
well,
grand scheme of
excellent
things,
then.
how much does it really matter?
Well, a small error can actually, I actually, so this didn't work for me for a second reason. And that was because down here, these two resistors, the one that's connected to the pin over here, the infrared receiver pin, what I had there by accident, let me see if I can get it into the camera's view again without making us too seasick. There we are. Okay, so this resistor right here was not red, red, brown. It was red, black, red, just like the one below it. I accidentally grabbed too many red, black, reds and not enough red, red, browns. And because of the fact that this one had 10 times the resistance it was supposed to, it didn't play nice with a resistor that happened to be inside this infrared receiver right here. This infrared receiver has a built-in resistor inside it. And having a larger resistor end to end with the one that was inside the infrared receiver ended up making it not work. So that was a second bug that I had to get out of the system. Now, usually if you happen to have, like for example, in a class I was teaching last night, we ran out of 220s, and so I used 200s instead, and that was no big deal. 20 ohms is not a big deal, but if you change it by a factor of 10, something unexpected might happen. How's that for an answer? We okay?
I think
Whoever
you
was
made
speaking.
circuits my least favorite thing, but
Oh
I'll.
no.
Well, I can't see them. I'm not young anymore.
yeah, yeah, I have an unfair advantage because I actually just take off my glasses to see them. But yeah, there's some cool little I'm not sure if it's a jeweler's loop is another thing you can use. I think I have one. I think I have a few of those handy. So a jeweler's loop looks like this, and you can just put it up to your eye to see those. And a magnifying glass is also another good thing to use. And there is additionally a little plastic hat where you can flip up and flip down a pair of glasses. That it's a hat with just a plastic rim. There's nothing up top, and there's a little pair of glasses that you can flip up and down that have nice high magnification so that you can see the resistors clearly.
So the
They
resistors
use
don't have a positive and negative like the bulbs and stuff do though, right?
That is correct. Yeah,
Okay.
the resistors will resist the flow of electrons equally regardless of which way you plug them in. You can unplug one, give it a half turn. Now that said, I do try to uh, whenever I'm constructing things to demonstrate, I do try to leave that gold bar on the right, and then that way I have the colored bars reading from left to right. Uh, and then, of course, in the documentation, in the pictures on the website, I also try to do that. But that's just for readability, as is the wire colors, since the color of the insulation around the wire doesn't have any effect on how the electrons flow through it.
How about organization? Um,
Or,
how
well,
do you
that varies. So, for example, our CEO has everything in nice drawers. There's my level of organization. So it's very much a what works for you thing. So for me, having it all and just kind of picking through it because you know picking through it is fine. For the vision impaired, oftentimes what they'll do is they'll buy a meter. Multimeters can be purchased for under $10, often at Harbor Freight, and then they will use the meter to measure each resistor, and then put a little masking tape label with the resistor's value written on it.
well, and the reason I'm asking is because this has already been a problem. Like, okay, guys, put the robots back in their garage, and then I find
Mm-hmm,
whiskers
mm-hmm.
on the floor. Or like I've already have kits all over the place that I don't know how they opened so many kits when I told them to pick one project to do. And now I have to go through and organize everything. So I need to keep like I don't know how often you work with students, but I need to teach them serious strategies for keeping this stuff organized, and it's probably 60% of the job.
Yes, I have noticed because I teach night classes, and my students need a fair bit of shepherding uh, with this kit. They're using the Cyberbot right now, and one thing that I do is I give credit for um, keeping their kits organized. Let me see if I can find the right page here. So it's on learn.parallax.com, and it's in the construction. So it's Cyberbot, and then it's in the build. Okay. Oh, okay. So this isn't the thing I'm looking for. I'll have to find you a link to a picture of all the parts, or Ari, maybe if you can find a link and paste it into the chat, that would be really nice.
Oh, I would love that because I could print that in color and put that in each of the bins, and then we could do inventory day, like at the beginning and
Yes.
end of a project.
Yes, don't make it your job, make it their job.
Well,
Now,
yeah.
another thing is there are those little plastic boxes that have little wells in them. Let's see, plastic organizer box, fishing tackle. So $7 at Bass Pro Shop is, here's an example of a, wow, Bass Pro Shop's website is slow. Anyway, here's an example of a box that is separated into little sections that fisher folk will maybe store flies in, or lures. And they can, if you add a box like this, and there are smaller ones too, if you're looking for just something to store a few of the small parts, although, now that I think about it, the number of compartments here, it's a little more than the type of parts we have, but not by far. So that kind of thing is also an option. Little plastic organizer boxes. Just doing a quick scan. I think this was more what I had in mind.
Yeah, because I'd like one where I could fit the remote in there too.
Oh, okay. Yeah, I mean, my personal favorite is this one right here. Why is it not showing me? Yeah, for some reason it's not letting me open it in another window, but I have quite a few of these where I put the robot in the top, and then I have a whole bunch of parts in the bottom. So this is a little bit large, I think, unless you have a really good sized cabinet for storage. Shoe boxes tend to be about the right size. And if you get a shoebox size and shape box, and if anybody wants to chime in with the name of what that box is called, like organizing bins, maybe, with a handle. Yeah, probably Sterilite is a good search to do.
Yeah, I was gonna do
Um,
a bunch of Ziploc bags, but I think this is a tackle box would probably be a better option, and they're not too expensive.
yeah, Ziploc bags do work. Yeah, yeah, just a trip to the craft store, or even say a Walmart, they will have various storage and organizing plastic bin. They probably have in a whole aisle. um, so that kind of thing. And then on Amazon, they'll have them too. And just search around for favorable dimensions, and that will hopefully help. Okay, how's that?
Photo boxes work too. To
What
put
boxes?
Um,
photos.
Photo boxes.
Yeah.
Photo boxes, very interesting.
Well, because they're small and you can keep some of the pieces in there. And Michael sells them a couple times a year where you have 16 small boxes in like one container. I keep my makeys in there. The one that you got, the I'm looking at your picture. It's the second row, first row, the bottom one,
First row, um,
or first column,
first
last
column. Oh, okay.
like that.
Oh, those are pretty nice. Yeah,
I keep my makeys in those.
I see. Okay. And then I use these personally. They're really not very kid proof though. They're just cardboard. All righty. Okay, so shall we continue on the triple checking of our circuit?
I have a quick question,
Go ahead.
Andy. So I don't know if you can see, because I'm catching up from the other night, I wasn't able to come. It might be a
Okay.
little blurry. The LED, I put the top that's supposed to be on that LED upside down. I don't know if you can, and I can't get it back off. So I've done it the reverse way.
Okay, okay.
Is there a way to get that off without breaking it? So like,
My guess would be that if you use a small pliers
Right.
to hold the legs,
yes.
that you can potentially get, yeah. Another thing I'd try would be hot water or even soap sudsy water. Might get in there and then allow you to twist it a little bit.
Oh, there it is. It's in focus now.
Yeah, it's
Yeah, I
very
did it
nicely in
upside down.
focus.
Yeah.
Wow. Yep. I would pull gently with holding the legs with the pliers and
Okay.
then pull gently. And then like I said, water, warm water, or even soapy, like dish soap water,
Right.
will not damage it.
Okay.
Ideally, if you can rinse it off with purified water,
Right.
that will prevent any rust from occurring on
Okay.
the legs.
Good to know. Thank you.
Yeah, and actually, in our manufacturing, there are little scrub brushes and containers of Dawn dishwashing liquid. Just so
Oh,
you know,
yeah.
it really is used in electronics manufacturing.
Yeah, I've got some Dawn in the kitchen. I'm going to pop over and grab some. Thank you.
Okay, sure thing. All right, anything else before we continue? Okay, then. All right, so I think we stopped at, where did we stop at? Did we stop at the or red, black, red, or did we stop at the brown or red, red, brown? Well, at any rate, check to make sure that your infrared LED's long pin is in the same row with the red, red, brown, the 2 kilo ohm resistor, and that its other end is plugging into P2. And then on P3, that should be going through a, okay, so red, black, red for P2. And then for P3, it's going to be red, red, brown. And then that's going to plug into the third row up with the same row as the lowest pin of the infrared receiver. Now, another detail is that your infrared receivers, there's a bump on the infrared receiver, and that is where the infrared light is allowed in. So make doubly sure that the bump on each infrared receiver, it's like a little hemisphere, is facing forward. So check that for both your infrared receivers. Okay, next up, the lowest pin on the infrared receiver that's on the bottom will go to the red, red, brown, should be in the same row as the red, red, brown 220 ohm resistor. And then that 220 ohm resistor will go into the P14 socket. Again, that's the black header that's next to the breadboard, and it's going to be the socket next to P14. I'm sorry, not P14, P13. So the red, red, brown resistor that's connected to the bottom pin of the infrared receiver here gets connected to P13. Then the red, black, red, the 2 kilo ohm, is going to plug into the top row with the long pin of the infrared LED, and then it plugs into P14. Last but not least, we have 5 volts going from the black socket above the breadboard and then arcing over, and that red wire is going to go and share a row with the topmost pin of the infrared receiver. There will be a blue wire that is just above that, second from the, we have the top row and then 1 row down from the top. That's where the short pin of the infrared LED is. And that's going to go, or that's going to have a blue wire that connects to one of the black GND sockets down below. And then there's also a black wire going to from the GND sockets up to the same row as the center pin of the infrared receiver. So the top pin is the supply. That's a red wire that goes to 5 volts. The middle pin is ground, and that's a wire that jumps down to GND. And then the bottom pin is the one that shares with a resistor. And that same thing should be on the other infrared receiver too, where we have the top pin with a red wire going up to a 5V socket. Then we have the middle pin with a black wire that's jumping down and over to GND. And then the bottom pin is the one that is sharing with a resistor. So if we've got all that checked out, the next thing we can do with caution is to turn on the power. The reason I say with caution is because in the event that there's a short circuit, in the event that inadvertently somehow a GND connection has been wired directly to a 5-volt connection, that's a short circuit. So basically all the electrons will rush through the wires from 5 volts to ground, and there won't be any power left to run anything. And if that happens, when you turn this 3-position power switch on, none of these lights will come on. So if you set the power switch from 0 to 1 and the light doesn't come on, immediately switch it back to 0 and look for errors. Now, that said, your error might be either that your battery isn't plugged in all the way, which is kind of an innocuous one. And then another innocuous error would be simply that not all the batteries are plugged in, or maybe they're plugged in backwards or something like that. So those are 2 other causes of the one light not turning on when you turn on power. So let's all try that now, being ready to switch it back off immediately if we don't see the light come on. And I have also a speaker plugged in right down there that is announcing the start of the script, which is this one from the kit. That's optional though. All right, so let's get some thumbs up. Hopefully everybody has nothing in front of the robot, at least nothing in its field of view. And their green light is on, and they've got 2 amber lights on, indicating that the infrared receivers don't see anything. Okay, I got 1 thumb up. 2, 3 thumbs. Whoa, 4 thumbs up. Good, good, everyone. 5 thumbs up. Well done. Okay, anybody need 6 thumbs up? Nice work. Anybody need some extra time, or should I move on? I don't know how many of you are following along with the circuits. And Okay, well, just unmute yourself and give me a shout out, or text Ari if you need some extra time. Otherwise, I'll move on. So we have 2 amber lights on. So the next test is to put your hand in front of the infrared LED on the right side of the robot, this being the right and this being the left. I know in the screen, it's the lower of the 2 LEDs. And so you should be able to put your hand in front of it and see the light go off, and then take your hand away from it and see the light go on. And then that applies, if you can do that for both, like if you put your hand in front of the left infrared LED, not too close, but if you're 1 inch to 5 inches away, say, it should cause the P20 light to turn off. And then if you put your hand in front of the right LED, it should cause the P21 light to turn off. If you've got both of those tests passed, go ahead and give me another thumbs up, and we'll be ready to move on to navigation. Okay, we got 1 thumb up. Two thumbs up, 3 thumbs up. Very good. I think I may actually see a 4th. Can we make it to 6? 5 thumbs up. Very good. Six thumbs up. All right. So let us try the next step then, which is going to be, you know what? It looks like you guys really managed to jump ahead, because I don't think I even pasted in the script. Sorry about that. I'm sorry?
Done a copy and paste there.
Oh, thank you. Yeah, so the script is linked to the slides, and of course it's also in the chapter. So like I could, for example, just continue to the next page here, which is test the infrared object detectors. And then this tests one of them. And then this test, which Dana pasted in, tests both of them. And so this one shines the infrared light, and then let's zoom in on this a little bit. So this statement right here is responsible for the left infrared LED, and it's a built-in method. So we say bot of 14, and that's the LED pin, and then 13, that's the receiver pin, the 2 that are connected to IO pins with resistors, and then .IR detect. And 3750 is the rate, the number of times per second that the light has to flicker in order for the receiver to actually detect it. They didn't want to just see solid infrared, because the sunlight can do that. But the sunlight light doesn't typically flicker. Now, that said, one thing that does sometimes flicker inconveniently at this frequency is certain fluorescent lights. So we actually have a whole activity about testing the fluorescent lights in your classroom to make sure that they're not blinding your infrared detectors with a constant barrage of 38 kilohertz infrared flickering. And this 3750, I'm not exactly sure why we did that. I do know that back in the day for our basic stamp microcontroller, it worked out better, but technically we should be sending 38,000. It's not far enough off to make a significant difference. And you can also use frequencies that are further from 38,000 to detune the to make the system more nearsighted. Anyhow, so this this grabs a 0 or a 1, 1 meaning not detected or a 0 meaning detected, and it places it in a variable named IRL for infrared left. And then this one does the same thing, returns a 0 or 1, and then it places that in IRR. And students will have to be careful about their capitalization here, because we use lowercase IR and then uppercase L. And if they made the mistake of using a lowercase L elsewhere, it might seem not to work. I just saw this in my night class where a student had that mistake and they couldn't get their bot to work. So be careful about capitalization. Then we have write digital, and that is what turns the P20 light on and off using the result from the previous statement here. So IRL receives a 1 or a 0 up here, and then we take that 1 or a 0 to turn the P20 light on or off, and then likewise with the P21 light and the other infrared detector. Okay, let's see here. So now what we can do is we can try out a script. Okay, so we are all the way to here now, and then this is the next one. And for some reason, no, that is correct. Looks like we've got the right script here, but that's not the right script. That's a little bonus script. So we'll go to the page and paste you the roaming script. This is called fast IR roaming. What I'm doing is I'm skipping the one where it roams exactly the same way as Whiskers does. Did you already paste it into the chat, Dana?
Yeah, but I can't get the drop off to work because my color, the next one, I tilted them down because does it have to do with color? What is it detecting exactly?
Well, it's detecting the reflection of a flickering infrared light. And so electrical tape usually does a pretty good job. If you have like 5 pieces of electrical tape edge to edge, that usually does a pretty good job of absorbing that infrared light. Black cove base along the bases of between the floor and the wall is another common absorber of infrared. And also large distances are an absorber of infrared. And so what she's asking about is, let's see, here's the check for IR interference activity where we run a script and point our robots up at the fluorescent lights in the room. And then adjusting the detection range. I think I'd better use the contents. So we're looking at the drop-off detector here. So this takes a little bit of tuning. Here's a little video where it's
so would the white and black make a difference?
Okay, so what it is this apparently our carpet it's dark enough and diffuse enough that it does not reflect the infrared, whereas the white poster board definitely reflects the infrared. And so normally what I do is most black or many black acrylic paints will absorb infrared nicely. So you can, for example, take a piece of poster board and essentially make the outer 4 inches or 5 inches. You can paint it black, or you can put electrical tape on it. Let me see if there's a picture with this.
Okay, yeah, no, you totally answered my question, because my desk is like a shiny black. So I'm not, it's having
so it
trouble.
Can't see it.
Right. So it's having trouble detecting when it's going off because it's all black. So okay. You answered my question.
That's potentially handy though, because if it can't see your desk surface, you can simply put a piece of paper or a piece of poster board on your desk. And then as long as there's a nice wide margin around the edge of the desk, then it will look like a drop off without posing the same level of danger that an actual drop off does to your bot. Okay, good then. Yeah, I don't know where my picture, I had a picture in most other texts of the course. Simulate drop-offs with poster board. So here we go. So here is, this uses 3 stripes of electrical tape, but I really do think that 4 or 5 are better. And like I said, acrylic paints, the thing to do is to buy an acrylic paint, a black acrylic paint, and then try it out on the poster board. Just put a little smudge of it on a poster board, or even just a piece of paper, and then point your infrared detector at it. And if it doesn't see it, then hey, great. And then we have this nice script running where it turns on the amber lights to let you know if it can see it or not. And so I actually will check it. I'll go to, say, Staples or something like that, buy some acrylic paint, and right in the car, I'll have a clipboard, and I'll just put a little splotch of paint and check to make sure that the particular paint I bought is invisible, because some pigments are actually, even though they're black, they're highly reflective. There's certain color printer toners which are black, but man, they are just bright as can be as far as the reflection of the infrared light goes. So far, I haven't had any trouble with any acrylic paint I've tried, but it's best to test it out before you get too far away from the store. The ultra wide Sharpies also work great. Just careful not to use them on your pen board. I did that the other night and found out that if you draw over it with I did that by accident the other night, and then found out that if you draw over it with a Sharpie that just looked suspiciously like an erasable pen, if you draw over it with a erasable pen, then you can erase it, which is handy. And then alcohol works too. But generally try to keep your Sharpie apart from your erasable markers. Okay, so here we are with the infrared, and what I'm going to do, as always, is slow my robot way down so that it stays in the field of the document camera. And we'll see how this goes. So I'm just slowing all my servo speeds way down and then hitting send to microbit. And now this script does not have anything for the lights. You can certainly add code to make the lights go in addition to this, and that's a good project for the students. But this doesn't have the lights, so I can't tell anymore if it sees an object or not. So what I'll do next is demonstrate this. Let's see here. Okay, I think we've got some room. All right, so it's not doing anything because I have the 3-position switch set to 1, which is just for that cuts it doesn't give power to the servos until I set it to 2. It just gives power to the rest of the board, which is what we used for testing. Okay, so now if it sees an obstacle, it turns away from it. Let's see if I can find a better obstacle here. How about the Cyberbot box? And as you can see, it's going to turn until the infrared detectors don't see the obstacle anymore. It basically checks 50 times a second. Whenever it sees an obstacle, it adjusts its it adjusts its turn. Now mine is a little close, and so if I want to make it detect in a wider range, I'll just point the infrared flashlights just a little further apart, and then we'll see that it avoids the box by a slightly wider margin. Well, it didn't actually seem to avoid it by a much wider margin. I'll just move the detectors out a little bit more. It's avoiding the box that my document camera is sitting on. Anyway, that's what you're looking for. So can I get some thumbs up if you were able to get that to work? You may have had to unplug your robot because it's going to move. Well, I mean, it's only 75. I got 3 thumbs up already. Very good work. 4 thumbs up. Excellent. 5. All right. 6. Congratulations, everyone. So that's pretty neat. I have a quick Easter egg for you. There's 2 different flavors of infrared following that are not documented, but they're kind of fun. This first one, I think, is more for displaying distance, and it might actually be too large for the Zoom chat. Oh, it appears to work. Nope, it's not letting me paste that in. Okay, so I'm going to instead paste in a link to the slide, and what you can do is just grab it from the slide, and the way to do that is to simply point at the bottom of the slide. You'll see a little bar right at the center base of the slide, and you can just drag that up to expose the teacher notes, and then you can select all and copy, and then go over to your script and paste it in. Let's see here. And there's one adjustment you need to make when running this. And what that is that, okay, I'm actually, because of the fact that we need to make adjustment and we're coming up on break, I'm going to paste in a different script. This one's shorter and it should work straight out of the box. I probably should have pasted this one in first. Okay, so cancel that. Let's do this one, and then we'll play with the distance detection display afterwards. So there is a following script. And so I'll go ahead and paste this in and reduce all my numbers so that hopefully it'll demonstrate nicely on the screen. Oh, actually, this is going to be a bear to adjust. So hopefully it'll just work. It's going to be kind of jittery because it's so as you can see, it's kind of turning back and forth, but it does successfully follow my hand. I'm noticing that this one tends to favor turning to the left a little bit. So if I take the right LED and put it further out, oh, maybe I need to take the left LED in. And I'll just try pointing straight forward first. Oh, that's much better. So I pointed the infrared LEDs mostly straight ahead, and it allows me to have it follow my hand, albeit not that well. The next script, after some tuning, will work a bit better, but this one does work. And if if you set the power switch to 1, you can then put your hand in front of it and you can see the measured distances on the as little bars on the microbit. And with this particular technique, your distance detection is actually in a very tight range. It seems like over about an inch, I'm able to make the bar go all the way down to 0 if I move my hand about an inch forward. And as I slowly move my hand about an inch backward, the bar will gradually increase to full distance. The next one is going to have a much larger range, but like I said, it takes more calibration to get it to follow your hand. So we can try that out and also take a break. So it's 5 minutes past the hour. We'll go ahead and resume at 10 minutes past the hour. Okay, welcome back everyone from the 5-minute break. What I did during the break was tested the following code, and I basically slowed it way down, and I think that is going to help. Although it looks like I might have slowed down the wrong one. Bear with me a second. I'm going to check and see which code I adjusted. Yeah, okay. So let's see here. I adjusted from -25 to -10 on this KP value at the beginning of the code. And again, I'm going to paste in the slide where you can open up the teacher notes or the slide notes. And so you can go to that slide and then drag the separator up to the slide notes. And I just updated the KP value near the top of the script to -10. And then taking all that and then pasting it into my microbit Python editor and hitting send to microbit. What that's going to do is just make it much slower. But at the slow speed that it's doing, it doesn't jump around quite as much, and you can definitely demonstrate that it is following you. And with some tuning, it'll probably follow you more quickly. But this I think is fairly satisfactory as a demonstration of the following capabilities of a more sophisticated script that is playing some electrical tricks on the infrared to get a distance measurement. In this case, what it's doing is it's changing the brightness of the infrared LEDs and then checking to see whether it detects an object or not at 5 different LED brightnesses. And then those are used to give us, again, not a very wide band of distance detection. And I'll talk about a distance detection device that will give us a much, much higher distance measurement coming up in a little bit here. But this one is satisfactory for basic following of some kind of leader, even though it's a little bit slow motion. Okay, did anybody get that one to work? That's kind of an optional extra. It's something you can try out. And again, I pointed the infrared LEDs a little bit outward. I think maybe about 15 to 20 degrees away from the center line. So if this is the center line, we're about 15 to 20 degrees out for each of the LEDs. And I'm noticing that the left sensor is more sensitive. It disappears. The line for the distance detection disappears more quick before the right one does. So if I point the infrared light outward a little bit more for the left and point the right one forward a little bit more, well, now I've gone the other direction. I've got one disappearing before the other, and there is some software calibration. There are some numbers you can adjust right inside the script, but I'm just trying to see if I can get it with just a little bit of adjusting the LED directions so that they disappear at about the same time. There we go. Okay, so those are disappearing now at about the same rate. And now it's going to track pretty well. I don't even need to adjust my hand to kind of help it follow me. It'll just follow as without really any assistance from the object it's following. Okay. And then the other way that it can be adjusted is with these dimming constants here. You can actually just say, well, I'm going to make this one dimmer by, say, 30 or 60 or 90 or 120, and then likewise with the other one. So whichever one seems to be brighter, whichever one has its detection stripe disappear first, you can make that one dimmer. So this is the right light that's disappearing more quickly. And so so I could, instead of adjusting the positions of the lights, simply increase the dimness of the right light. So those are unpublished, but some of the students might find it to be really interesting. So I wanted to show that to you. What do you think? Is that kind of cool? And did anybody get it to work other than me? I've got a thumbs up. Whoa, all right, way to go. six straight out of the gate there, very nice. Okay. All right, so that is it for the hands-on portion of the Cyberbot workshop. So again, we want to unplug the power to conserve batteries and to conserve batteries. So I'm unplugging the power here, and then also unplugging the USB cable from my microbit. Okay, so let's talk a little bit about some of the other things that you can do with the Cyberbot and the microbit. Starting off, one of the ones in the stock kit, so the kit that you have also has sensors for visible light navigation. Ah, boy. So we updated our learn.parallax.com site, and I thought I had everything updated properly in the slides. Let's see if this one works. Okay, so this one went to the right spot, but this one didn't. And if you have course materials that need to be updated because our website is updated and we had to use different addresses for the various chapters, what you'll want to do is, for example, if you know the name, like we could do visible light, so we could go to learn.parallax.com and search for, let's try visible light cyberbot. Okay, and here it comes up, visible light navigation for the cyberbot. And now we're at that front page, and so you can then update your student materials so that they get to the right spot again. Paste. And there we are. Okay, so for visible light navigation, it introduces phototransistors as a light sensor. And these favor red light and then off into the infrared spectrum as well. And then the light sensors look like this. They're the ones with the flatter, these are called phototransistors, and they have a flatter top. And so the chapter goes into building a simple light sensor to understand, for example, how automatic lighting works when things get too dark outside. And then the lights automatically come on, and how a phototransistor circuit works. And it goes into Ohm's law and how the current through a resistor results in a voltage measurement that can be used. And there's a really cool park in the dark activity where the cyberbot will go and if you have a box, like if it goes into a shoebox, for example, it'll detect that everything just got really dark and then stop moving as though it has automatically parked in a garage, which is kind of a fun one. And then there's a clever trick that can be done where essentially it's a different circuit that uses capacitors, and capacitors are like little tiny batteries that store charge. And then these phototransistors, depending on how much light shines on them, they will drain these capacitive batteries either more quickly or more slowly. And so what the script does is it uses the same kind of statement that would turn a light on if a light circuit were connected to an I/O pin, and it instead sends that 3 volts, connects that 3 volts to the circuit. That charges up the capacitive battery. Then this becomes an input, meaning that it monitors the circuit but has no effect on it. So since the circuit has just changed and it's lost its supply, this charged up capacitor parentheses battery will lose its charge either more quickly or more slowly through the phototransistor, because the phototransistor will conduct more current when brighter light shines on it, or less current when dimmer light shines on it. And so using this method, it gives a much wider range of sensitivity that allows the cyberbot to respond similarly regardless of the brightness level in your room, direct sunlight notwithstanding. Direct sunlight is just too bright for the system. So we usually tell, there's some instructions in here to close the blinds and avoid direct sunlight when you're working with this. And it is kind of fun. You can, for example, turn off all the lights and then open the door. And if sun is streaming in, you can have the whole swarm of cyberbots make for the door in order to get to the bright light. So that's pretty fun. And then this is what it looks like. So here we have our cyberbot roaming along in kind of a uniform light environment, and then a cell phone flashlight is going to be turned on and shined in front of the cyberbot. And it goes ahead and follows it away. The light was actually shining right on one of the 2 sensors to make it turn like that. Another shot of the part 2 light following system. And then this is from the page helping students build it. Next up, there's some cool additional sensors, or no, I'm sorry. So these, again, this is just a recap of the sensors that are used on the Cyberbot. There's the whiskers contact sensors, there's the visible light spectrum sensors, and then there's the infrared object detectors. Now, in addition to that, there are activities introducing circuits that I talked about on Wednesday, and also sound. Few other things. Navigation control from a keyboard is a fun one. And my goodness. I know I correctly updated these. I'm not sure why the changes didn't take. Okay, well, at least we got it here. So I've still got a few corrections to make in these slides. All right, hopefully those are now fixed. Let's try this one. Yeah, we're good. All right. Anyway, so keyboard control and tilt control. Both of these have radio control options, and one additional thing they do, in addition to just providing some fun, is the control happens in the example scripts unencrypted. And so that allows, that makes an opening for cybersecurity lessons where students can learn to protect the data that's going between, say, the microbit that's transmitting keyboard entered navigation commands and the Cyberbot, so that they can't have their information easily obtained by other students as a network hardening approach. So let's take a look first at keyboard control of the Cyberbot. So one fun thing to do is to start with all the Cyberbot robots in the classroom on the same channel as a microbit that's connected to this computer. And the microbit that's connected to this computer is running a script where it's essentially talking with the serial monitor, and it's asking for a left wheel speed, a right wheel speed, and then an amount of time to maintain those speeds. And what it does is when you type in those numbers get transmitted back to this microbit receives them, and then it radio broadcasts them to all the microbits that are on the same channel in the classroom. And the result's kind of cool. So here we're typing in the numbers for the left, right, and runtime. And then after controlling all the Cyberbots, then students tend to get paired off into groups, and each gets their own radio frequency, and they can go from there. And so this one starts tethered, where you're actually just typing in, you have your Cyberbot connected by a USB cable. And then after getting that working, then there's an activity where, first of all, you as a teacher can control all the Cyberbots in the room, and then the students can pair off and have remote controlled Cyberbot robots. And there's also tilt control, where you can either take a microbit or a Cyberbot that has a microbit in it and load in a tilt controller script, and then load in a tilt controlled Cyberbot script into the Cyberbot, and that will that will allow you to tilt your microbit to make the Cyberbot go in various directions. So here we have our controller, and keep an eye out as you're watching this script. You might notice that as the controller microbit is tilted, there's a little clock hand that's going to be pointing in various directions. And for there will be an identical clock hand on this microbit that will point in the same directions as this one does, indicating its tilt. This clock hand is going to essentially point roughly in the direction a small, say, ball bearing would roll off the microbit as it's tilted. And so if you tilt it straight away from you, it's going to roll this way, and the little pointer will point straight down, and so on and so forth. And in addition to the lights, the Cyberbot robot is also responding to the tilt with wheel speed adjustments. So the further they tilted it sideways, the faster it turned. And if you tilt it away from you, it goes forward. If you tilt it towards you, it goes backwards. That's a fun one. Students inevitably try to set up robot wrestling with that. So we've actually published a robot sumo with the Cyberbot activity that I'll show in just a second. So hopefully these ones actually connect. Okay, so this is cybersecurity now. And so with the Cyberbot, we now have a couple of applications that are worth protecting. And there's a lot more that are introduced along the way. There's, for example, a countdown. There's sharing something personal by pressing a button to send a smile or a frown. And so for cybersecurity, there's two approaches. There's with the Cyberbot, which is a somewhat expanded version, and then there's the microbit only version. And so, so we have links to the main Cyberbot with Python page, and then a subset that are mostly microbit activities. And so here we have in the prerequisites, this covers all the computer sciencey stuff in the Cyberbot lessons with lots of Python scripting exercises covering strings and dictionaries and exception handling and communicating through a terminal. And then also your scripting basics up here with writing microbit programs. Then in the main lessons, well, we've got all the Cyberbot basics, the circuits, the sound, the navigating by whiskers, the navigating by light, the navigating by infrared. Then there's a radio basics chapter, a data with radio chapter. And then we have the navigation from a keyboard and navigation with tilt, because those both build off of the radio basics and the radio data. Then we get into encryption and how to use encryption to foil sniffing attacks, and how brute force can be used to break weak encryption keys, and how to strengthen your encryption keys. And then there's another one, which is malformed packets that we don't see here, but that when we go to the Cyberbot series, we then have down below here at the bottom, after brute force, we have malformed packet attacks and defenses, which is one of my favorites. I'd like to mention that some of these can be done with make code as well. So the Cyberbot robot, all of the basics like the contact switches, the circuits, the sounds, the infrared, the light navigation, have equivalent make code block coding versions. And there are some equivalent, like we've got the keyboard navigation and the tilt control, and we have the encryption intro and the brute force attacks and defenses. We don't have sniffing or malformed packet attacks and defenses in this area. And then there are even the extras down below. There are some extra projects, and they're not shown on this slide, but this has some extra projects too, and I'll get to that shortly. Now, we also have a cybersecurity only. So this is the microbit only version of the cybersecurity series. And so if we follow this, we see a pared down list that doesn't have all the cyberbot stuff. So this is a microbit only. And so we have the basics of all the computer science lessons here. And then for our main lessons, we start out with radio, basics in radio data, which was down the road in the cyberbot tutorials, but we just dive straight into that and then do the encryption, sniffing attacks and defenses, brute force. Here's our malformed packets. There's also some cybersecurity in our AI with the microbit lessons. And again, we have similar, but this is simply selections out of the cyberbot. We don't have for the make code block coding language, we don't have a specific cybersecurity page, but these are all essentially from the cyberbot page. So you can just basically pick and choose from the cyberbot page if you want to do microbit only lessons. There's also a cybersecurity tutorial series. Well, that was what I just showed, but there's an on-demand workshop where you can essentially, if you have an extra microbit on hand, you can just dive into it right away, because we have the 3 videos, which are just like the 3 videos we've recorded for this one. There's 3 videos for cybersecurity and a set of presentation slides. So like if we go to the on-demand workshop by following the link, I should probably paste that one in to the chat. Copy, paste. All you have to do is scroll to the bottom and you'll have the links to all 3 2-hour videos and the presentation slides. And you can just go through those. Or you can apply, and you already have 1 microbit, so we would send you a second microbit if your on-demand self-paced workshop application is accepted, which it likely will be since you made it here. You can apply for this one. We'll send you a microbit to work with your cyberbot, assuming that we haven't already sent you a second microbit at some time previously. Let's see here. This malformed packets is kind of fun, and it's an example of how it starts with the microbit only. Like, for example, one of the things we do earlier on is a countdown timer. And so when we do malformed packets with a countdown timer, the idea is that we can create a packet that sends something the microbit isn't expecting, and that causes an exception, and the script just freezes when you do that. And so essentially, if you start the countdown, sorry, somehow I made it to malformed packets and defenses. Well, that's, sorry, let's see here. I made it to malformed packets and defenses, but we're in the share something personal area. Okay, that's fine. In the share something personal, what the script does is it allows either student to hit a button, and it starts out with a check mark or an X or a heart, and then there's also a skull. So if you send the check mark X or heart, the other student or however many are on the same radio channel, which is a thing that's configurable in the script, by the way, and the cybersecurity lessons go into that in detail. So like if you do the self-paced course, you'll see all about that. Or if you just read into this, you'll see how the script sets the channel so that Students can be paired or in groups of 3, etc. At any rate, so when one student hits a button and then they'll use the A button to scroll through their various options, and then the B button to send, and then any other microbits that are on the same channel will update their display to whatever the most recent student sent. Well, there's also a skull option, and when that is selected and sent, what it does is it sends a malformed packet, one that the receiver microbit can't parse and make sense of. And like web pages that freeze on you, if you've ever had that experience, the microbit will also freeze on you until you restart the script. And that is an example of the, the kind of damage a malformed packet can do. And so then there's a remedy to that, which primarily involves a technique called exception handling, which is scripting that handles an exception by checking to see if anything goes wrong, and then either reporting that something went wrong, but continuing to run the script as opposed to just freezing up because the script didn't know what to do. And so students will then modify their script, adding in exception handling and seeing that the skull no longer has the negative effect on their microbit. And one other example then would be from keyboard control. So essentially with keyboard control, we have the same kind of problem where if there's some malicious scripting going on, where a numeric value in this case is replaced by a string, and then the receiving microbit is still expecting a numeric value there for the number of milliseconds to execute the maneuver, again, an exception occurs and the microbit stops functioning until it's manually restarted by pressing and releasing its reset button. And in a robotics contest, that doesn't work so well for students. And so they practice how to use exception handling again to prevent this kind of problem from happening. If they get garbage data, the script doesn't halt, and that's an example of hardening your network for malformed packets. And then there's also encryption, which is included in here as kind of a finalizing the set of lessons. So they have something that's encrypted and can handle malformed packets. And then there can be contests where where essentially attacks are foiled by good defensive scripting. There are also add-on devices that can be attached to the Cyberbot robot. 3 really common ones are this little turret that has an ultrasonic distance sensor on it. I said earlier I would talk about higher resolution distance sensors, and this is the one that I was referring to. There's also a line following kit where you attach little line sensors that go close to the surface the Cyberbot is rolling on to detect a line and follow it. You can also, there are variations on this. For example, you can create a road and stay on the road, or you can create an all black background with a white road or a white line and follow that too. All of which takes some adjustments to the script. And then there's also a TV remote version, because I mentioned earlier that the infrared LED lights and infrared receivers that are that come with your Cyberbot kit, they respond to TV remotes. The receivers do, and the LEDs are the same. So the LEDs, the infrared LEDs, are the same ones you would find in a TV remote, and the infrared receivers are the same ones you would find in your television. This light and receiver system is also found in things like automatic faucets. So when you put your hand under the faucet has a system that's sending out the infrared light, and when it bounces off your hand when you put it under the faucet, it goes to the infrared receiver, and then that's what turns the water on for you, or that's what causes the microcontroller to know your hands are there and to turn on the water for you. So here is the line follower kit. It's included in a class pack, so that's part of the class pack. And in fact, all 3 of these systems are included in our class packs, which are 12 packs with extra parts and extra rechargeable batteries and battery rechargers for the whole class, or for a class set of 12 robots. And so, so here is our line follower. And it can also be purchased separately if you, for example, wanted to purchase just the Cyberbot robots like the one you got in the mail for this course. You could selectively add QTIs, for example, or you could selectively add the infrared remote kit, or you could selectively add the ping ultrasonic distance sensor with the turret. Let's see if we have any cool videos on these. Maybe under following a line. No, I thought we had a video there. Sorry about that. Surely we have it for the ping ultrasonic. Here we go. So it just turned away from the camera after the ultrasound reflected away from the camera. Now it's going to see the wall. And that's a lot of fun. Okay. Next up are some other fun ones. Like here's a, you remember the tilt control earlier? Well, there's a sold separately gripper. This is not included in, this is just a strictly sold separately item. There's no class pack. Well, there is a class pack of 10 grippers, but there's no class pack that includes Cyberbots and grippers. At any rate, what this does is it allows you to press the A and B buttons on the tilt controller to open and close the jaws of the gripper. There's the A button, there's the B button, and then there's the tilt control. And we'll go and grab a 3D printed cylinder and deliver it, and then park. So that's kind of a fun little application. And another fun one is I mentioned when we were talking about straightening out the path that your robot travels in, that there are servos that are aware of their angular position. They're called, we call them feedback 360 servos. And watch closely this little white line on the wheel as the script is executed for forward, left, right, and backward. By the way, these are relatively high speed too. And I didn't quite stop it at the right instant. There we go. So notice that it's pointing downward. I set it to go for 1 entire revolution. And then after turning left or turning right and then left and then right again, we are still pointing downward and then backing up and pointing downward once again. So that's an example of how a positionally aware servo can be used, and it can definitely straighten out your Cyberbot robot's travel as well. And so that's a sold separately item where some classrooms choose to swap out the original servos for the Feedback 360s. They are a little bit more advanced for programming. They don't follow along exactly with the statements. So there's a whole section on how to change existing statements to work with the Feedback 360 servo. So I recommend that as like a later on thing. And also these servos still have a slight margin of error, but if you even have a tiny margin of error when you turn in place after you've traveled for 10 feet, that's going to be a fairly large error. So it's not the be all and end all, but it is a really nice little system. And this is the page with the gripper on it, and this is kind of a fun one. Okay, for some reason, yeah, this is just the tilt-controlled Feedback 360 servo gripper. What I'd like to show you is the, let's see if I can find it fairly quickly. There is a YouTube video where when we grab an object with the Feedback 360 servos and measure, go and get an object with distance control. Here we are. So this one used measurements and then some calculations to code how many revolutions, basically the arc length of a wheel of a full turn, and how many of those, or how many 64ths of a full turn are needed to get to the object, and then to set it on this little post-it that's on the table up here. So it's another application of using the Feedback 360 servos. And a pretty good challenge for the students. Adding a little math to the lesson. And notice that it did go back to the same spot that it started in, unlike some of the stuff we did earlier. Okay, electronics. To take a deeper dive into electronics, we have what's a microcontroller for the microbit. And a couple things I'd like to point out here is one, that there's a lot of extra visual support. So for example, if you're lecturing on a breadboard, there's a nice little video that you can actually open in another tab, and it'll talk about the various rows and columns on a breadboard, and how the coordinates of a particular socket work, and then later on the internal connections. So here we have the columns, and then there's another video later that talks about how to connect two wires together, and how not to connect two wires together. Lots of stuff like that to support the more difficult topic of electronics with the microbit. And so we have a little adapter that plugs the microbit into a breadboard. And there's lots of extra cool stuff that can be done here, because we have some software called the Cyberscope. It's at cyberscope.parallax.com. And what it does is it allows the microbit to behave like a voltmeter. So basically, the microbit measures voltages, and it sends data to the cyberscope.parallax.com web app after it's connected. So you'll load a script into the microbit, then you'll disconnect the editor from the microbit, and then connect the cyberscope to it, and it will show you voltage measurements. And here we're demonstrating Kirchhoff's voltage law, which states that the voltage increases around a loop are the same as the voltage drops. And so the 3.3 volt supply voltage adds up to the measured voltage. So 3.26 volts in this case adds up to the measured voltage across the resistor plus the measured voltage across the light emitting diode. And so that's a nice example of one of the lessons. And then later on, we use an oscilloscope to monitor the we use the microbit as an oscilloscope in conjunction with the cyberscope application to graph the voltages over time with a signal going to a servo. So this is the same thing. You could also use this to examine more closely the signals going into the servos on our Cyberbot robots. And so this is a basic lesson in how oscilloscopes work and can be used to measure, in this case, the control pulses that actually tell the servo where to turn if it's a standard servo, or how fast and in what direction to turn if it's continuous rotation. Additional resources, I just added a list of helpful links here. A reminder that the student lessons are at learn.parallax.com, as are the educator resources. And also a reminder that we have our workshop page, and that you can go there for past, present, and future workshops. So if you follow the parallax.com/category/events link, which I'm about to paste in, that takes you to the upcoming events. And right now we're thinking about, well, we've got some, in Palm Springs, we've got the CUE conference. We have an open house in May, and then we've got some edu chats where you can come and learn what we're up to, what's the latest. And then we have cyber.org, lots of other, and CSTA, that's one that many of you might be going to. And then down at the bottom, we have the At Your Own Pace workshops. And then also, if you want to look at past events, you can click the Past Events tab and see what was done previously, what was recorded previously. This is a reminder of the Make It Code It site that we talked about on the first day, and we did the step counter. There's lots of other things for the students to do there. This is a link to some of the older documentation. Again, I mentioned earlier that the microbit Python editor has its documentation built into the left side panel here under reference, and also API. But there is some older documentation, and it's a pretty good read. And so it's nice to have two different takes on things. Another resource for the microbit and the cyberbot is cyber.org. Their mission is cybersecurity and developing a cybersecurity workforce. So they have some cyberbot content and some additional cybersecurity with the microbit content. You can, if you're a United States teacher, K-12, you can join. And after you've done so, you can get into their Canvas system, which is for the teachers, not for the students. And you can download slide decks. Let's see, it's slide decks, teacher notes, and student handouts. and there's a cyber literacy section that takes a little bit deeper dive into some of the computer science and cybersecurity stuff. For example, they have AES 128 encryption as an example, whereas our site doesn't quite go that deep into encryption. We stay with some of the older classical stuff. And then we have a little bit more in the cyberbot realm than they do, quite a bit more actually. Their cyberbot material is fairly terse compared to our web pages. So you can mix and match resources, and that might be helpful. For purchasing the cyberbot, you can simply go to this link right here to purchase it individually, or I guess I'll paste that in. And then we also have the class pack, which is a little bit more than 12 cyberbots purchased. It's a little bit more than 12 cyberbots because we include the line follower, the ultrasound on a turret, the rechargeable batteries, the TV remote, the battery chargers. So those are all part of the 12 cyberbot class pack. And so it's a little bit more than 12 individual cyberbots using the previous link. You can also upgrade from a BowBot or an Arduino Shield bot to a cyberbot. There's a conversion kit, and the link's in the slide for any of you who might need it. Replacement parts. These are invaluable. Definitely get a few electronic parts kits to have extra to replenish, and likewise with your screws, nuts, and etc. I realize it's 5:01. I'm almost done. The thing that I must have skipped the slide is to talk about the educator resources. So I'm going to pull up, I'm going to go and show you the login. So if we go to learn.parallax.com and then follow the educators tab, there's a login link right here. Okay, now I'm already logged in on a different page, so I'm not gonna log in here because I want to show you that if you're in the educators tab and you go to cyberbot resources, for example, you'll see the publicly visible stuff, teaching strategy guides, these slides, the standards matrix for the cyberbot. Those are all downloadable, and I'll give you this link. But the assessment material, as you can see down at the bottom, is locked off. And so you can log in to get to it if you're approved as an educator. We verify educators who apply to get a login at learn.parallax.com. We sent you all logins, so now you can log in, and it's simply following that login link. And then so here is what the site looks like after logging in. Okay, so here is before logging in. And then if I go to educators and cyberbot resources, here is what after logging in looks like. So instead of this lock and message, you get a link to the assessment materials downloads. And so, for example, if we wanted to look at sound, we can download a zip file for the sound chapter, and then open that up, and you'll see a PDF and a Word doc in the zip file. And I guess I need to unzip this here. I'll just copy it and then go up into my downloads and then paste, and then open the PDF with my browser. And here we have some multiple choice and matching and fill in the blanks, and then some coding challenges. And then careful, make sure not to print out the red answer key material. Keep that for yourself and just print out anything that's not red. And that's an example of how to access the educator resources that are now available to all of you. Okay, and then very quickly, we have a slide with all our support. Our email is education@parallax.com. That will go to me, Ari, Ken Gracie, and a couple of other folks. And basically, we decide amongst each other, if you have a question, who is the best person to answer your question, and we jump in and answer it right away. And you can also use this for purchasing inquiries, although going directly to sales@parallax.com works too. If you're kind of sure what you want, if you want to talk about it, education@parallax.com, or you can call the educator hotline and ask there as well if you have questions before purchasing. We also have forums and a Facebook page, and so these links are all here for you to help out. Education@parallax.com is really good. If you have an urgent tech question, the educator hotline will work. Yeah, the educator hotline would be the best one to call for that. Okay, well, that's it. Thanks for coming today, everyone, and thanks for staying a few minutes over. Sorry about that. I hope you all have a great weekend. This has been Andy Lindsay at Parallax, and thanks again for coming. And again, have a great weekend.